This question tripped a lot of people up in HSC, so grab a pen and some paper because I will be breaking it down for you step by step so you can understand how it works. This is the question 31 of the HSC Mathematics Advanced 2025 paper, and the question says, the equation cos px equal 1/2 has two solutions where x is in between 0 and 2 pi, and p is larger than 0. Find all possible values of p. First, we want to aim to understand the question in one reading. Although this question does not give you a lot of information, there's still a lot of mathematical clues that you want to translate into plain English so you can understand what the question is asking you for, what concept is it testing you, and how to solve the question. Right away after reading through the question, you should notice that the question has given you two unknown variables, which are p and x. With p being the coefficient of x, we can tell that this is testing the concept of transformation of function. Specifically the understanding of horizontal dilation, which in this case, horizontal dilation is applied to cos x by a factor of p. And I want to explain how horizontal dilation works here. You might have heard teachers saying horizontal dilation is stretching or compressing a function across the x-axis. But what does this actually mean? A horizontal dilation is basically when we keep all the y values exactly the same for a transform function, but we increase or decrease all the corresponding x values by a multiplication factor. So this means that all the original y coordinates is exactly the same as the transform y coordinates, but the corresponding x coordinates are not equal to the transform x coordinate. So let's have a look at a generalized case. The most simple form of a function is y equal f of x. And we want to call this x x1 to indicate that this is the original x coordinate. To see the effect of a transformation on the x values, we want to rearrange this equation to make x the subject. So applying inverse operation, we can write x1 equal the inverse function of y. Now let's apply a horizontal dilation with a factor of 1/2 to compress this function horizontally. First, we want to write out the exact same function as before, and we want to call this x x2 to indicate that this is the transformed x values. And to apply the horizontal dilation with a factor of 1/2, we want to put a number 2 in front of the x, but within the bracket. To see the impact of the transformation on this x value, we want to rearrange this equation to make x the subject of the equation. And applying inverse operation, we have 2x2 equal to the inverse function of y. And we have x2 equal to the inverse function of y divided by 2. Here you can notice something. x1 is equal to the inverse function of y. x2 is equal to the inverse function of y divided by 2. So we can sub x1 into this equation here and make it x2 equal to x1 divided by 2. So simply we just sub x1 into the inverse function of y. So in this form, you can see how the transform x coordinate was impacted by the transformation. x2, the transformed coordinate of x, is 1/2 times smaller than the original x coordinate. So this means that in the transform function, all the y values would stay exactly the same as the y values in the original function. However, all the corresponding x values would be 1/2 times smaller than the original function. We can see how the transformation reflects visually on the graphs of the function. So let's have a look at the graph of y equal cos x. Y equal cos x is shown here. So this one is y equal cos x. And we can also have a look at the graph of y equal cos 2x. If you notice, y equal cos x between 0 and 2 pi, which is this domain here, you can see a complete cos wave here. But for y equal cos 2x, within the same domain, 0 and 2 pi, we can see two complete cos wave there. So you can see how the horizontal dilation, when applied, would compress this function horizontally. Another thing you can notice here, if we put a function y equals 0.5, which is a horizontal line, it crosses the first function exactly twice in y equals cos x. But for a compressed function, the same graph, y equals 0.5, would cross this compressed function 4 times. Now, let's circle back to the original question. The question gave us a condition that says find all the possible values of p when cos px has 2 solutions in the domain of 0 to 2 pi. What this question is asking you for is, if you look at the graph of the original cosine x, within the domain of x equals 0 to x equals 2 pi, we want to find a horizontal dilation factor of p in cos px that gives exactly 2 solutions for x when cos px equals 0.5. For you to better understand, I will explain how we approach solving this question. We want to solve the equation cos px equals 0.5 for when x equal 2 pi. Because this is the latter end of our domain x, and x cannot be any larger than 2 pi. Subbing x equal 2 pi will yield the following equation. Cos 2 pi p equals 0.5. And what does this mean? This means that we want to find all the values for p where cos px crosses the line y equals 0.5 at exactly x equal 2 pi. When solving for p, in cos 2 pi p equals 0.5, it will yield many values for p. And remember, p is the horizontal dilation for cos px. So that means that it could yield a small value for p where the cosine graph is so stretched out that it only crosses the line 0.5 one time. So that one time will be exactly at x equal 2 pi. Or it could yield a larger value for p and compresses the cosine graph so that it crosses the line y equals 0.5 many times. So it could do something like this. So if you can see here, it crosses that line many times, but it will always crosses the line y equals 0.5 at x equal 2 pi. It just depends on what the value of p is that determines how many times it crosses y equals 0.5. So our goal here is to find a value for p that compresses the cosine graph so that it crosses the line y equals 0.5 at 2 pi as the third time. So that means it would look something like this. So as you can see here, the graph would crosses that line 3 times, but the third time would be at x equal 2 pi. Because any value of p smaller than this would compress the graph enough that it crosses the line y equals 0.5 less than 3 times, which is 2 times. That matches the condition that the question gave us. Now that we have that explained, let's dive into solving the question. Let's sub x equals 2 pi into cos px equals 0.5 and solve for p. Here we would solve this equation like how we would usually solve a trigonometric equation. First, we define our domain for px. So the domain for x is 0 and 2 pi. So the domain for px would be between 0 and 2 pi p. Next, we consider where does cosine equals 0.5. Let's draw a Cartesian plane here and recall our all station to central. So all station to central. You can see that cosine is positive in quadrant 1 and quadrant 4. So in quadrant 1, cosine equals 0.5 when the angle is pi on 3. So let's draw that here. And that's pi on 3. So here we can write 2 pi p equal pi on 3. That's the first answer. Cosine is also positive in quadrant 4, and the angle would be equal to 2 pi minus pi on 3. So right here. And that one would be equal to 5 pi on 3. So far, within 0 to 2 pi, we have two answers for 2 pi p. But if you notice, the domain here is between 0 to 2 pi p. 2 pi p is an undefined value, which means technically there is an unlimited number of answers for the value of p in this case. However, Remember that the value of p must stretches or compresses cos px enough that it crosses y equals 0.5 exactly 2 times. Here we sub x equal 2 pi in cos px equals 0.5 to solve for p as the horizontal dilation. This means that whatever value of p we find, let's say p equal a, when we sub it back into cos px equals 0.5, we will generate a solution at x equal 2 pi. This also means that the order of the answers for p indicates the number of solution we will find for cos px equals 0.5. I will explain this in a bit more details, but in the meantime, let's find a third solution for 2 pi p. Let's get rid of this and find a third solution. So the third solution would again be in the first quadrant, and it will be equal to 2 pi plus pi on 3, which equals 7 pi on 3. And you can choose to include this symbol here to indicate that there could be more answers to 2 pi p in this case. And we will solve for p here. So p here would equal 1 on 6 as the first one, and the second one would be 5 on 6 and 7 on 6. And you can use this symbol again to indicate that there are many values of p's that we can find in this case. Now we want to sub the values of p back into cos px equals 0.5 to find solutions for x. And then we can count how many solutions each horizontal dilation p generates. So first, let's sub p equal 1 on 6 in cos px equals 0.5. To solve this equation, first we want to define our domain here. So x is between 0 and 2 pi. So therefore, 1 on 6x would be between 0 and pi on 3. So now we can write 1 on 6x equal pi on 3. And as you can see, pi on 3 is the limit in our domain here. So we don't have any more answers for 1 on 6x. And x here would equal to 2 pi. So what the graph would look like is it is so stretched out that it crosses that line, y equals 0.5, exactly once. And that one time is at x equal 2 pi. Now let's sub p equal 5 on 6 in cos px equals 0.5. So we would get cos 5 on 6x equals 0.5. And to solve for this, again, we will define our domain. X is in between 0 to 2 pi, and therefore 5 on 6x is in between 0 and 5 pi on 3. From here we can write 5 on 6x equal pi on 3 and 5 pi on 3. So 5 pi on 3 here is our limit of the domain, so there's no more answer that we can find for 5 on 6x. So x here would equal 2 pi on 5 and 2 pi. Let's have a look at the graph again to see what this would look like. So here you can see that the horizontal dilation of p equal 5 on 6 would compresses the cosine graph more and generates two solutions for cos px equals 0.5, one at 2 pi on 5 and one at 2 pi. All right, so let's test our last value for p. We would say sub p equals 7 on 6 into cos px equals 0.5. So that would give us cos 7 on 6x equals 0.5. And again, we want to define our domain. X is in between 0 and 2 pi. 7 on 6x would be between 0 and 7 pi on 3. From here, we can write 7 on 6x equals pi on 3 and 5 pi on 3, and the last one is 7 pi on 3, which is our domain here. And there's no more solution for 7 on 6x. So x here would equal 2 pi on 7, 3 pi on 2, and 2 pi. The graph for cos 7 over 6x would look like this. Again, you can see that the horizontal dilation of p equals 7 over 6 would compress the cos px graph even more and generate 3 solutions for cos px equals 0.5. First, we want to find the 2 pi line on the graph, which is here. And as you can see, the 3 solutions are here, here, and here. So circling back to this part here, the first solution to p generated one solution to cos px equal 0.5. The second solution to p generated two solutions to cos px equal 0.5. And the third solution to p generated 3 solutions to cos px equals 0.5. So the fourth solution to p would generate 4 solutions for cos px equals 0.5, and the fifth solution would generate 5 solutions to cos px equals 0.5, and so on and so forth. So to conclude this question, we will write, therefore, p is larger than or equal to 5 over 6 and smaller than 7 over 6. This is because with horizontal dilation, p being equal to 5 over 6, that's when we generate at least 2 solutions to cos px equals 0.5. And at 7 over 6, we generate at least 3 solutions to cos px equals 0.5. So therefore, when p is between 5 over 6 and 7 over 6, we generate at least 2 and less than 3 solutions to cos px equals 0.5. A final note for this question here. So, when studying for a math exam, there are 2 main things you should focus on, and that is your understanding of the concept and your exam techniques. Your exam techniques include things like timing strategies, for example, what question to answer first to maximize your marks and your times, how to present your answers to save time on writing, and many more things. In terms of presenting your answer, I have attached a downloadable PDF of the solution down below. You should utilize mathematical symbols to communicate where you can to save on writing and be more precise with your answer. In terms of your understanding of the concept, this question requires you to understand the topic of transformation of functions very well, which hopefully you have now after watching this video. If you are interested in understanding it on a deeper level, comment down below and let me know if you would like a video on transformation of functions, and let me know if you want a video on exam techniques as well. If you have any questions, feel free to comment, DM me on Instagram, which is linked down below, and send me an email. I'm more than happy to answer any question. That is it for today, and I hope you enjoyed the video. Until next time.